Okay, thanks everyone for headed right back. So we're ready to start our program again. So we're going to start off with Dr. Bob Howarth from Cornell University.
Thank you. Thank you. Thanks for the invitation to speak, and thank you all for coming today. I have a bunch of co-authors here, and I particularly want to acknowledge Tom Butler, who's in the audience over there, Dennis Swaney, Roxanne Marino as well. All of the field work I'm talking about today was done by Tom Butler, and most of the synthesis was done by Dennis Swaney, and I'm just the point person, the PR specialist, if you will. We also have some EPA colleagues, and you'll see how their work comes into this. So you've heard already from Charlie that the watershed for Skaneateles is small relative to the surface area of the lake, and it's very small and far smaller than any of the other Finger Lakes. And based on that alone and the fact that people have been trying to protect the watershed for some time, you'd expect that there'd be relatively low nutrient loading from the watershed, and I think that's true. That's why it's such an oligotrophic lake. But we're interested in the airshed, what's coming in through the atmosphere, and we're particularly looking at ammonia gas because it historically has been understudied, and we think it could be important, and I hope to convince you that that might be the case. The airshed, of course, is much larger than the watershed, and there's a lot of agricultural activity upwind of Skaneateles Lake, so the question we're posing, is that important as a nitrogen input to the lake? Now I want to explain a little bit why we're interested in nitrogen, and I want to make clear that we do not think that nitrogen is regulating the growth rate of phytoplankton, including the toxic cyanobacteria in the Finger Lakes. The Finger Lakes are all clearly phosphorus limited. We've known that for a long time. Just give me a couple of examples here. Bruce Peterson, PhD from Cornell in 1971, clearly showed that Cayuga Lake is phosphorus limited, and my student Brian Roberts, who got his PhD in 2004, showed that Skaneateles is phosphorus limited. You'd expect that. The inorganic N to P ratios are 1,000 to 1 or greater across all of the Finger Lakes. So why am I interested in nitrogen? And it's because we think nitrogen might play a role in the blooms, not by encouraging the growth of the organism, but by prolonging their lifespan, lowering their mortality. So this is a simple model that we're starting to pull together. And basically, as I say here in the box, there are two ways to bloom. You can grow fast or you can live a long time. And the growth rate is clearly regulated by phosphorus and also light and mixing dynamics of those things. And that's all important. But we think that the mortality term there is a function, I say zooplankton here, biomass, but also benthic mussels are undoubtedly important as a mortality term. And the biomass of those filter feeders is important, but so is the toxin concentration in the microcystis. And there's a fair amount that the actual relationship between grazing and microcystis is not particularly well known, microcystin, but we do know that with increasing inorganic nitrogen supply, the organisms produce more of the toxin. So there's a reason to be looking at nitrogen and seeing how that might be changing over time. The Finger Lakes are all pretty naturally nitrogen rich. Nitrogen's probably increased over time, but the native bedrock is nitrogen rich. Nonetheless, nitrogen levels have gone up, and we are speculating that the direct input of ammonia might play a role as well. So we've been looking particularly at the input of ammonia to Skaneateles, directly to the lake and to its watershed, since about 2021. And we've been looking at the Connecticut Hill monitoring station, NADP monitoring station for ammonia since 2008. And for those of you who don't follow atmospheric deposition much, that station is one of the oldest continuous NADP monitoring stations in the country. It was set up originally by Gene Likens when he was at Cornell and has been run by Tom Butler since 1976. So long historical data set there, but ammonia wasn't measured until 2008, and ammonia is still undermeasured, understudied across the country. So we use passive samplers to measure ammonia, and this shows a little upside down cup there. It's just a a filter inside there that absorbs ammonia gas onto it from the atmosphere. We put them out for 2 weeks at a time, we being Tom. And then the analysis is done by the NADP lab in Wisconsin. And what else do I need to say about nothing, probably? We've been measuring, again, at multiple stations across the Skaneateles watershed, but also at this long-term monitoring station. And here, we're looking at the ammonia concentration over time from 2008 to 2024, and you can see that it's going up. This is a regional signal. We don't entirely understand why the ammonia is going up. I can try to address that a little bit if people have questions, either after the talk or over lunch. I think it's a very interesting thing. Our stations in the watershed for Skaneateles are shown here, and we have several in the southern part of the lake, the less developed part of the lake, and several in the northern part, just more developed and also closer to some of the upstream, upwind agricultural sources. We also have some data from sites in Owasco, but I won't go into any detail on that today. So this is our first year's worth of deployment. We started in May of 2021 and went for basically a year, so you can see a strong seasonal pattern. We're showing each of the sites here. They all sort of track one another, but the concentrations are significantly higher at some of the sites than at others. There's a lot of interesting data in this temporal trend, and again, I can go into that in questions if you'd like. Based on these initial results, we're able to get some renewal funding for a more extended campaign, and this shows all of the data. So starting back there in May of 2021, and we finished sampling this past May. The blue line there at the bottom is the regional signal from Connecticut Hill, the NADP monitoring site. All of the sites in Skaneateles are higher than that, some of them a great deal higher. They all show the same sort of seasonality. Now these are concentration data. What we want to know is the input to the watershed and directly to the lake surface. And to get that, you take the concentration and you multiply it what's called a depositional velocity, and you have a flux rate. And for depositional velocity, this is where our colleagues from the EPA have played a role. We're showing here by week number, so starting in January, over a year. Most of that top curve there is our estimate for the depositional velocity for the lake surface, and there's some seasonality there that's driven by wind. The depositional velocity is higher when it's windier. The other curves are pulled out of the EPA CMAQ model for what the depositional velocity would be in this area at any particular time. Strong seasonality in that as well. A lot of that is driven by humidity and also by canopy cover of trees, which will increase absorption. So we use these estimates times our concentration data to come up with estimates of flux. And here are our estimates. We're looking here averaged over time for an annual average deposition rate for each of the sites in the Skaneateles watershed. The red are our estimates based on our measurements. The blue bars are what the EPA would estimate the input is based on their national CMAQ model. And on the far right is our estimate for the direct deposition to the lake surface itself, which is higher than anywhere in the watershed. So a take-home point here is that there's a lot of spatial variation across the watershed, and our estimates are all, almost all, higher than what the EPA classically would think. So it's a pretty high input. Another way to look at that is we're looking here at the direct inputs of nitrogen from the atmosphere to the lake in 2023 on an annual basis. And both of these bars are based largely on the EPA, CMAQ, and TDEP models. But the difference between the left bar and the right is that on the darker bar here on your left shows what the EPA, dark blue there, would think for the direct gaseous ammonia input to the lake. And the stippled bar on the right is based on our estimates with real data for ammonia concentration. So again, EPA has historically been underestimating the ammonia input. It's quite substantial to the lake. The other major bars there, the biggest points are ammonium, the ionic form in wet deposition, and nitrate in wet deposition. So from that, we can put together a nitrogen budget for the lake inputs. And the direct deposition to the lake from ammonia is 18.3 metric tons of nitrogen per year. Other reduced species, ammonium ion, are lower at 12, and the oxidized inputs are 11. So the major input directly to the lake is, in fact, ammonia gas. We also have substantial nitrogen deposition to the watershed. The ammonium there is 67.4 metric tons. Other inputs are lower. And we have an estimate of what NANI, that's nitrogen use for human activity in the watershed would be. So agriculture as well as oxidized nitrogen inputs and use in human food, sewage inputs, things of that sort. And from that, we can estimate what the watershed load is. So overall, the watershed load is greater than the direct deposition, but the direct deposition to the lake surface is high. And again, a lot of that is as ammonia, which is extremely biologically available. So indeed, if the cyanobacteria are using that to increase their toxin load, that number is important. Now we took one more step and tried to look at where the ammonia is coming from. And for that, we used the NOAA high split model. So on the left here, you're looking at the lake, and the red dots are CAFOs, confined animal feedlot operations, large ones, and these are all large dairy farms, basically. And also shown are our sampling sites. So we're using a high split model to look on a real-time basis for the time that our samplers are out there over 2 weeks. We look at the wind on a real-time basis, look at where the wind has been coming from 1 hour before it hits our actual samplers. And if it's coming across one of those CAFOs at that time frame, we call that a hit. And we can then plot the hits as a function of the concentration that we're seeing for each of those times. And the most convincing part of this plot is on the far right over there, which shows our data for the summer. The ammonia concentrations are higher in our samplers when the wind has been coming more over CAFOs. So it's an agricultural source. In the fall and winter, it's less convincing, same trend, but of course the deposition is lower. And then we have that little messy plot up there in the spring, but it turns out that the late spring numbers look just like summer and the early spring numbers look just like winter. So the bottom line is when the wind's coming over CAFOs, there's more ammonia going into the lake and into its watershed. And that has been going up over time. So that's my ammonia talk. I would just want to end with some information, not going to show any data on this, but we've been working with a series of colleagues, mostly from Canada. Irina Creed from the University of Toronto is the lead on this, working with Josh Teenpoint from York and John Small from Queens. Several of us from Cornell got them interested and engaged in it. And we're also working with Anita Dedick from Mostar University in Herzegovina, and with Doug Young, who's the owner of Spruce Haven Farm. And we cored 6 of the biggest Finger Lakes back in June at fairly great depths. You can see the cores there. This is mostly Joshua Teenpoint's ability. We've taken those and sectioned them in the field at half-centimeter levels, and we have already dated them. We can share those data soon. We have data on chlorophyll from all of the lakes. We have data also so far on one of the genes that's a major precursor to producing microcystin over time, and we'll be sharing those data as they come along. We also intend to measure the microcystin toxin itself. Phosphorus, we'll be looking microscopically at when microcystis came in. We'll be looking genetically at when microcystis came in. These lakes are all historically under-monitored, but we're hoping this will provide a background record across the Finger Lakes on that. And we'll be very happy to share any of those data as they come along. I want to give a special shout out here to Doug Young, because he owns one of the CAFOs that we think is responsible for this ammonia and maybe aggravating the blooms. He really wants to know if that's true or not. And when he found out that we wanted to sample these lakes back in June and that we needed a boat, he volunteered his boat, which is the one there, and he towed it from lake to lake for us and piloted us with great skill, allowing us to take these cores by hand at water depths of well over 100 meters in some cases. So anyway, very proud of that. So that's my talk. We're funded by the USDA Hatch formula funds to Cornell, and also by the gift from Mr. Atkinson that supports my salary and other activities in our lab. And we have to thank a lot of people for giving us access to their land, for putting on ammonia samples, including Charlie Driscoll. So thank you, Charlie. Time for questions? I'm told there's time. No questions? Yeah, in the back there.
What do you think the residence time of ammonia is in the lake once it's deposited? How quickly does it get oxidized to?
Well, it's probably has a very short residence time, and I won't say exactly how long, but I would think, you know, minutes to hours, not days to weeks. And it's I think it's more likely to be taken up biologically by the phytoplankton as opposed to oxidized. I mean, there are organisms that'll oxidize it to nitrate if nothing takes it up faster, but they tend to be pretty slow at that in a system like this, particularly in an oligotrophic setting. So very short. It's highly labile. And of course, you know, one of our thoughts is that it might make it easier for the microcystis to produce the microcystin. I have to say that there's not a lot of strong lab data on that. The few studies where people have looked at nitrate versus ammonia, it doesn't really seem to make that much difference, and yet it seems like it should theoretically. So I'm hoping more people will get interested in doing it, but it's a significant input. Good question.
Hi, it's Lewis McCaffrey from New York State Department of Environmental Conservation. Thank you. That was a fantastic presentation, Dr. Howarth.
Thank you.
I wondered where you got the information about all Finger Lakes are nitrogen rich. We don't see that constant across the lakes. That was one question.
Okay.
The other was, have you tried looking at nitrogen isotopes for source identification?
Yeah, no, both good questions. On the isotopes, no. We have not done that here. My lab has historically done it in coastal systems and elsewhere, but not in the Finger Lakes. And I'm not aware of anyone who's done that yet in the Finger Lakes, but that would be a very important thing to do. As to
Great idea.
the data on the nitrogen-rich lakes, it's coming in part from your CSLAP monitoring and others. But the nitrate, if you look at particularly the inorganic nitrate to SRP ratios, it's on mean values across the lakes always more than 1,000 to 1. TN to TP is lower, it ranges from like 120 up to 300 to 1 or so, but I think it's the inorganic ratio that's more informative there.
Thank you.
Bob, great talk. Thank you very much. If you will, and if I've got time, maybe two quick questions. One is, and this is just sort of speculation, but at our site, we measured deposition, wet and bulk deposition, and I find actually surprisingly high concentrations of phosphorus in that. And I wonder if you had any thoughts on phosphorus sources. It would be largely in a particulate form, but from CAFOs, and do we know much about that? And then the other question is, I mean, the atmospheric chemistry has changed a lot over the last couple decades with declines in sulfate and nitrate, and that's going to influence the processing of ammonia in the atmosphere. Right. So could you speculate on how those changes have altered the transport and availability?
Those are both great questions. I don't think there's much data to suggest that the ammonia input to the atmosphere has increased all that substantially in our area over, say, the last decade or so. So ammonia concentration's going up, but not necessarily the inputs. Could be due to changes in farming practices, but I think a lot of it could be, as you say, because the atmospheric sink has gone down as sulfur's gone down. The residence time of ammonia in the atmosphere might be longer. It's also related to the weather. Every time it rains, it's going to strip all the ammonia out. It's related to the humidity, and those things are changing. So I think there's some great research that could be done on that. I don't have the final answer, but, I alluded to the fact that we don't really understand why that's going up. I don't think it's a simple source attribution. On the phosphorus, we didn't measure it. I think it could be very important. It could be, it's going to be particulate, as you say, and one culprit could be dust from plowing and all. But I think there's some evidence too that pollen can be a big source of particulate phosphorus as well as nitrogen. And, we'd have to look microscopically to get at that probably.
Yeah, very few measurements of atmospheric deposition of phosphorus.
Very, very little. I think it's an important point. And probably pretty labile too, although it depends on what it is. If it's pollen, it'd be less so than if it's agricultural soil ending up in the lake that way. Great, thank you.